Okay, so we reached this point where we use the row column rule to get a product matrix. So we say that the matrix should be how we number of rows here should be equal to the number of columns should be equal to the number of rows. Okay, let's look at another example. Example 4. Example number 4.
Easier for you to see if I sit here.
So the first one, if A is a 3x2 matrix and B is a 2x4 matrix, then what is the size of AB? What is the size of AB? So solution, if let's say we have our A here and then we have our B there, then what is our AB here? So what is our AB? So if A has the number of rows in A are 3 and 2 there, then it should be equals to the number of rows in B. The number of columns here should be equals to the number of rows in B, which is 2 here, and then we have our 4. Then what will be the product? So what will be the product? What will be our AB? Yep. So if you take this one out and this and this, so it will be 3x4 there. So the product is 3x4. So it will now be 3x4 matrix. 3x4 matrix. Same thing to this number B. If A is 3x4 matrix and AB is 3x6 matrix, then what is the size of B? What is the size of B? So you do the same thing. So we have here A is 3x4, and then we are looking for B, and then this will give us AB. This AB is 3x6. So what will be B? So definitely, since the number of columns should be equal to the number of rows, then there is 4, and here would be what? 6. So B will be 4x6 matrix. 4x6 matrix. So the next example, we're going to see how A by B equals to 0. And in this case, A is not equals to 0 and B is not equals to 0. So there's an example, there is an example in which A by B equals to 0, but A and B is not equals to 0. And also we have an example where AB is not equals to BA. AB is not equals to BA. So let's look at these examples. So example number 5. 5. Let A to be equals to 1 0 0 0 and a B equals to 0 0 0 1. Show that AB equals to 0, although A is not equals to 0 and B is not equals to 0. So this is one example in which AB equals to 0 and A and B are not equals to 0. So the solution is just the product, which is AB, which is equals to 1 0 0 1 0, and then our B is 0 0 0 1. Then the product here will be 1 multiplied by 0, which is here, plus 0 multiplied by 0. The next entry will be 1 multiplied by 0, and then 0 plus 0 multiplied by 1. The next one is 0 multiplied by 0 plus 0 multiplied by 0. The last one there is 0 multiplied by 0 plus 0 multiplied by 1. And this would give us what? 0, 0, 0, 0. This would give us 0, 0, 0. Example number 6. Let A to be equals to 1, 2, 3, and 4, and B equals to 2, 1, 4, and 3. Show that AB is not equals to BA. AB is not equals to BA. So this is another example, special example in which AB is not equals to BA. So the same way, so 1, 2, 3, 4. So let's calculate AB, which is equals to 2, 1, 4, 3. And when we solve this, then what we get is we should get 10, 7, 22, and 15. So that is the product for that. And BA is equals to 2, 1, 4, 3, and A is 1, 2, 3, 4. And the broad product here is 5, 8, and then 13 and 20. So you realize that AB is not equals to B. It's not equals to B. Another example in which AB equals to AC, and whereby B is not equals to C. So let's look at this example. So example number 7. Let A to be equals to 1, 0, 0, 0. B equals to 0, 0, 0, 1, and C equals to 0, 0, 0, negative 1. Then show that AB equals to AC, although B is not equals to C. So we cannot use the cancellation rule here. So we cannot cancel A and A. So in this case, the same thing, happens, the product. So AB equals to 1 0 0 0, and then this is 0 0 0 and 1, and this we got this one as 0 0 0 and 0, right? AC is the same thing, 1 0 0 0, and then 0 0 0 -1, and this will still get what? 0 0 0 and 0. So shows that AB equals to AC, but B is not equals to C. So you cannot use the cancellation rule. Cancellation rule in this case means that here AB equals to AC. What you can do here, you can multiply by the inverse of A and the inverse of A here. So A inverse is the same as what? Identity, which is multiplied by B, equals to identity multiplied by C. And in this case, B is equals to C. So this doesn't happen for this case. So it doesn't happen. So that is the cancellation rule. We will look at that later in our class. Okay. Let's look at the properties of matrix multiplication. Properties of matrix multiplication. And this is 2.3. If we let A be M by N matrix, B to be N by P matrix, and C to be P by Q matrix, and R be a number, and R be a number. We have those matrices there. So for A to multiply by B, then this should be equals to. For B to multiply C, then B should be equals to. This will be the number of columns should be equals to the number of rows in the other side. Then property number 1. If A, property number 1, A multiplied by B, C is the same as A, B, C. So you can actually multiply A and B, and then later on you multiply by C is the same as multiply B and C, and then you multiply by A. Sorry. Number 2, A and then B plus C is the same as distributing A here. So you can distribute AB plus what? AC. You can distribute the matrix. Number C, A plus B, C, you can also distribute C inside here as long as, so you can say A, C plus B, C, where C is N by P matrix. C is N by P matrix. Then number D, we have R and A, and then we multiply by B is the same as multiplying AB, and then later on you multiply by R. R is a number. And then number E, if we have the identity, which is IM of A is the same as the A there. And this is the same as, this is also, you can multiply A by IN. It is the same as A. It is the same as A. And so those are the properties. Those are the properties. 2.4 definition. If A is an n by n matrix and K is a positive integer, then A raised to K is the same as A all the way A, and these are K times. So you can actually multiply A raised to K is the same as multiplying those matrices K times. So multiply K times. For example, example number 8. If A equals to 1, 2, 0, 2, 0, 3, and then 0, 3, and 4, then find A raised to 3. Find A raised to 3. So this is the same as A raised to 3 is the same as A multiplied by A multiplied by 1, A. And you can use the properties up there. So you can actually multiply A, and then later on you can come and multiply by A. Okay. And this is the same as multiplying A by A is 1, 2, 0, 2, 0, 3, 0, 3, and 4 multiplied by 1, 2, 0, 2, 0, 3, 0, 3, and 4. And then also multiply by 1, 2, 0, 2, 0, 3, 0, 3, and 4. So you can multiply the two of them first here, and what you get is 5, 2, 6, 2, 13, 12, and 6, 12, 25. And then you come now and multiply by 1, 2, 0, 0, 2, 2, 0, 3, and then 0, 3, 4. And finally, what you get here is 9, 28, 30, 28, 40, 8, 87, and then 30, 87, 136. So that is what you get. Do not expect something like this in exam. You will not be using a calculator. So this is just for your reference. Any question after that? Okay, if there is no question, let's now come to the next section here, which is section 3, and this is the transpose. For matrices. Transpose for matrices. So what do you mean by the transpose? Let's look at definition 3.1. So the transpose of an, let's say, M by N matrix A is the N by M matrix, which we always write this one as AT, right? That's A raised to T, obtained by interchanging the rows and columns in A. So if A is an M by N, then our A transpose E will be now N by M. So you just obtain that one by interchanging the rows and the columns. For example, example number 9. If we let A to be equals to 1, 2, and then 3, 4, or B to be equals to 1, 0, 2, negative 1, and C to be equals to 1, 2, 5, 3, 4, and 6. Number A, find C transpose and C transpose transpose. Find C transpose and C transpose. So what is C transpose? C is a 2 by 3 matrix. So the transpose of that should be 3 by 2. So C in our case is equals to 1, 2, 5, and then 3, 4, and 6. So our C transpose, and this one is 2 by 3. This one should be what? 3 by 2, which is equals to, you just bring this row to be the column. So it should be 1, 2, 5, and then 3, 4, and 6. So that is our C transpose. Just interchange the rows and the columns. Now, what about when you transpose this again? So the C transpose transpose. If this is 3 by 2, then it will now come back to what? 2 by 3. So you just interchange the rows and the columns. So it will now be 1, 3, 2, 4, and 5, 6. Now let's find A transpose plus B transpose and A plus B, and then we transpose A plus B, and then we transpose. So what is our A transpose there? So our A transpose is our A equals to 1, 2, 3, and 4. Our A transpose will be 1, 2, 3, and 4. Or B equals to 1, 0, 2, negative 1. Our B transpose is equals to 1, 0, 2, negative 1. So our A transpose plus B transpose will be equals to 1, 2, 1, 3, 2, and 4 plus 1, 2, 0, and negative 1, which is giving us 2, 5, 2, and so A plus B equals to 1, 2, 3, 4 plus 1, 0, 2, and negative 1, which is giving us 2, 2, 5, and what? and 3. So when you transpose A plus B transpose will be equals to what? 2, 2, and then 5, and 1, 3. So what do you see from there? Yeah, the same. So this is another property for the matrix. So this is actually the property of matrix transpose, which we'll write it later. Okay, now what about when you multiply? So when you multiply, if you multiply AB and then you transpose, so this is number C. Let's find AB transpose. Let's also find A transpose, B transpose, and also let's find B transpose, A transpose. Let's see which one of those are equal. Okay, so we have our A as 1, 2, 3, and 1, and 4, right? And then we have our B as 1, 0, 2, and -1. Then when we multiply that, what do you get? So when we multiply these, then what you get is 5 minus 2, 11, and minus 4. So this is actually AB, which is equals to that. Now, then AB transpose is equals to, you transpose this, 5, -2, 11, and minus 4. And then you do what? You transpose. And this is equals to 5, -2, 11, and minus 4. That is what you get there. Now, so what about A transpose, B transpose? This is the same as transposing A, which is 1, 2, 3, and 4 multiplied by 1, 0, 2, and -1. And what you should get there is 1, -1, 2, and 0. So that is what you get. That's what you get. Now, what if you multiply now B transpose and A transpose, then what do you get? So B transpose is 1, 2, 0, and -1, and then A transpose is 1, 3, 2, and 4. Then what you should get here is 5, 11, minus 2, and minus 4. So that is what you should get. Then what do we see from the 3 examples there? This will lead us to 3.2, which are the properties of matrix transpose. Whereby if we let A, B be matrices and R be a number, then number A transpose, when you transpose this one, what do you get? Comes back, right, to A. You find A transpose, and then you transpose it again, it will come back to A. Number 2, and we saw that one in the first example. Number B, if we multiply A a constant or a number by A, and then we transpose it, it is the same as R, and then A transpose, or this is the same as A, R transpose. So you don't have to transpose R because it's a number. Number C, if A and B are M by N matrices, then A plus B, and then we transpose, is just the same as A transpose plus B transpose. This is what we just saw in example number B. And then finally, number D, if A is M by N matrix and B is N by P matrix, then A, B transpose is the same as B transpose A transpose. And this is what we just saw here. So if you transpose, like if you transpose, it is the same as interchange. The interchange is bring this B to the other side. So this one will also see it. This is actually an application of the inverse, which we will see it later, whereby A, B inverse, if we replace this T by the inverse, then it is the same as B inverse, A inverse. This is that. We'll just see that. Okay, any questions after that? Then the final example in this section is 3.3, which is a definition whereby an N by N matrix A is called symmetric if A transpose equals to A. It is called symmetric. A transpose is equals to A. A transpose equals to, for example 10. If we have A equals to 1, 2, 3, 2, 4, 5, and 3, 5, 6, then A transpose equals to transpose this. Interchange the rows. 1, 2, 3, 2, 4, 5, 3, 5, 6. And they are what? They are the same. So they are symmetric. They are symmetric. So this. Okay, that is the end of section 2.1. Okay, let's see the review. Oh. So did you get time to go through it? I know you guys were busy over the weekend.
I went through most of it, not all of it yet.
Still okay.
I didn't get home from work till like 10 last night. I had to tile the bathroom. I
Okay,
did some of it this morning. though.
so most of these we have actually covered, all of it actually. I don't think there is any which you can have an issue. So like the first okay, so before that exam is tomorrow, which is what is that day? 1, right?
Yep.
At 1 p.m. Actually, you can do it within 1 hour to 2:15 p.m. Same place, same venue, which is 3 or 4. Okay, I actually changed your syllabus, so I noticed that I don't know why I put it the last. I think I put it the last week for you to, which is the week of 14th, which is not actually the case. So the semester is ending the first week of July. So
To go.
yeah, you actually have a month to go. So the exam is on 7th, the final exam.
7.
So that is the last day. So I actually changed third exam to be, you'll just see it in the syllabus. I posted it yesterday. So make sure you check it. So the next exam is I think on 15th, and then the third exam is on the end of next month, which is, so the second exam is 6:15 and third exam is 6:30. Yep. And then the final exam is on 7. Yeah, just confirm it. Just confirm. Okay, so I'll always be so we'll be checking it before the exam, and then I'll always be pausing the video for the exam. So this is actually the reflection of what you will expect. Some of the questions here will be related to what you will get in your exam. Okay, number 1 there, is there anyone with any issue there? So number 1, you can use elimination method. You can use, so you can actually use elimination. You can also do what? Graph it, right? Oh, you can put it in matrix form. And then you get the what? Augmented matrix, and then you reduce completely to get a solution. So again, make sure you are so aware of the signs. Actually, most of the solution, most of the students usually have an issue with the signs, addition and multiplication, especially if you're multiplying the negatives. So you should be aware of that. And then again, when you're reducing completely, then make sure that the diagonal matrices are what? Are always ones, okay? So they should be 1. And then when you're done with the echelon form, if you want to reduce it completely, you start from the one. You don't keep going up. You don't start by reducing the one here. So start by reducing. Okay. Number 2, find the elementary row operation that transform the first matrix into the second. That one, I don't think you have an issue with that. So what do you do there? So you, yeah, so R2 plus twice. Okay, determine whether so if you look at this, so the pivot position is here, the pivot position here, and the pivot position is there. So is this reduced? Yes, because these are zeros. Here, the pivot position is here, this is here, and then it's here. Is this one reduced? No, since we have not, this is a pivot position, so everything here should be what? 0. Everything there should be. Okay, number 4. Find all the possible values of this. I gave you in your worksheet. So you might expect something like this in your exam. So make sure you work on that. Actually, it is there. So let me not lie to you. Something like this is in your exams. So make sure you know no solution, infinitely many solutions, and unique solution. So let me give you a hint. For no solution, then the last row in the augmented matrix is what? Contradictory. And what do you mean by contradictory? It should be 0 if it is x1 plus 0 x2. Should give you a number here. Let's say a real number here. Should give you a real number. So this will give us what? No solution. No solution. For infinitely many solutions, infinitely many, then you should have what?
A free variable.
A free variable. And then finally, for unique solution, then all should be what? Basic variables. So they should be basic variables. So in this case here, the value of h for the unique solution can be any number. Actually, it can be 0 if so long as it is for unique solution, that should be having this variable. Yeah, but for it is like this one, I know you'll be given, you just be looking for h. In this case, it's okay. But for this, our h here can be any for basic. So it can be 0, it can be 1, something like that. Okay, it can be anything. Okay, any question up to the, oh, it was actually number 5. So number 4 is find all the possible values of h such that the given matrix or consistent. So for consistent, it is just the same as for consistency, it means that yep, it should not have a contradictory. So for this one to be consistent, here should not be contradictory. They can all be zeros. They can all be zeros, but this should not be any number, and this should not be a number. This, okay, for consistency. We have done number 5. Okay, find the solution set of the following linear system. But again, you can do what? You reduce. So it does to reduce echelon form, to reduce echelon. You can just write the solution. So basically, that's right. don't write. So you can just say for any x, x for those free variables. Okay, this is just similar to this. Again, here, make sure that you are considering the what? The signs for the coefficient matrix. For the coefficient matrix, make sure that you consider the sign. Okay, the next one, I think is just similar to this. So you just reduce it completely. So you get the solutions there. So you reduce actually complete to the solution. All right. Number 8 is very simple. And it's the simplest. You get something like that. I don't think you like waste a lot of time. So 8. I don't think you actually waste a lot of time solving that. Number 9, you can do what? You can write that one in augmented matrix form, and then you do what? And then you get the values of x1 and x2. So and then you reduce, you get the values of x1 and x2. Number 10 is a similar thing. You just reduce it. And then same thing for the homogeneous. For homogeneous, that would be the 0, 0, 0. So for the homogeneous, it means that this one is what? This one is just 0 for the homogeneous. So you'll just be having that one only. Because this will just be 0. B will just be 0, 0. Expect that one in your exam. Okay, number 11. Let's V that one. Does that span at 3 justify your answer? We did this one in class. So again, you get B, which in this case, this B can be equals to what? B1, B2, and what? B3. And then you do what? And then you write the augmented matrix there, and then you reduce. So definitely, you should not get what? A contradictory row. So it should be consistent. So in this case, what you do is, so you now write this one as 1, 0, 1, 1, 1, 0, 0, 1, 1, and then B1, B2, and B3. And then you do what? Then you reduce. So when you reduce, so you get that and that, all that. So the only thing you do is reducing that one. So so we can actually reduce this. So 1, 1, 0, B1, 0, 1, 1, B2, and then finally we subtract, right? So it is R1 to get a new R3, then R1 minus R3. So 0. It's taking time again. So this is minus 1, and this is 1, and this is B3 minus what? Minus B1. Again, you reduce again this one by doing what? By adding, right? So it is 1, 1, 0, B1, 0, 1, 1, B2, and then we add 0. This and this is 0. This and this is 2. and that will be B2 plus B3 minus B1. And looking at this, you have the pivot position in each of the row there. So it means that V1, V2, V3 spans what? Spans R3. Spans R3. Now, if this one was 0 here, and we have these values here, yeah, we have 0 here, we have these values here. So we cannot be guaranteed that all these values here will be what? 0. So it means if we have 0 here and we don't have, and we have this one, so it means this will not be consistent. So then it will not span. We have that one in our example that we did in section 1.5, if I'm not wrong. Okay, number 13.
Can we do number 12?
Number 12. Okay.
Because I'm getting the wrong answer or the answer is wrong.
Okay, let's do number 12. Maybe I put it the wrong answer there. Maybe I was solving my own things. So we have 1, 5, 8, 7. And then we have 0, 1, 1. Then we have 1, 3, 0. And then we have 2 minus 3. And 2 there. So what is the question there? Is B in the space of R3 spanned by the columns A? Okay. So what is the first thing you do there? Yep. So that is the augmented. Did I put the augmented matrix? Yes, I did it, right? So that is the augmented matrix. Then you do what? You can switch R3 and R1. So you get 1, 3, 0, 2, and then 0, 1, 1, -3, and then 5, 8, 7, and 2. Okay. And then the last one there. Our R3 will be R3 minus 5 R1. What do we get? So 1, 3, 0, 2, 0, 1, 1 minus 3. So this one is 0. 8 minus 15 is -7. 7 minus 0 is 7. 2 minus 10 is -8. Then the next one is our new R3 will be R3 plus 7 R2, which we get 1, 3, 0, 2, 0, 1, 1, -3, and then 0. Minus 7 plus 7 is 0. 7 plus 7 there is 14. Minus 8. Minus 8. Minus 21. So minus 8 minus 21 is what? Minus 29. Minus 29. So I was doing my own things, right? So it is actually what? Spanning it just there. So it spans R3. So it is spanning R3. So B is in the span of R3. Thank you about that. Guess it took you a lot of time to solve it. Okay. Let's go to the next. Number 13 is actually similar to number 12. you found 10, right? You found h minus 10, right? So when you solve it, you must find h minus 10 there. So for this one not to be consistent, then
is that kind of like 11 where you would be equal to B? Or is that considered an odd number?
which one is that?
13. Is that-
Oh, you said
So we're
Okay.
kind of handling that same as,
yep. So what? Yeah, you actually, actually you do it like number 11.
Yeah.
Yes. You actually do it like number 11. Yeah. So you make sure you put the B1, B2, and B3. Okay, number 14 is the homogeneous. Determine whether the following homogeneous linear system has the trivial solutions or non-trivial solutions. So it means if for the trivial solutions, they should be what? Basic variables. Basic variables. And if there are no basic variables, then the next step is to get the linear relation. So you need to get the linear relation. Number 15, same thing. If it is not basic, then we need to get a linear relation. I mean, if it is not giving us trivial solutions, then you need to get the linear relation. Number 16, determine whether the columns justify your answer. Just like number 11. So you need to put the zeros there at the last one as the augmented match. Since this one is what? Homogeneous. So you need to check whether it will be consistent or not. So you just reduce that. No, it's even clear here. You just do what? You just switch. You just switch R1 and if you switch R1 and R3, then you get what? Actually get that. Because all of them have the what? Basic variables. Yep. So it will be linearly independent. Number 17, those are the applications that we did. This is the easiest because if it is 0, 0, then it is. If we find one vector to be 0, 0, then it is linearly dependent. If it is like this one, linear combination of the others, then it is linearly dependent and others. Okay, number 18, find all the possible values of h such that the following are linearly independent. Just the application of what we just did up here. Application. Number 19, that is what we did last time. So if you let the transformation from R3 to R2 be the linear, then find the vectors of x in R3 whose image under T is B. So you just do what? Multiply. And then for x, you multiply by x1 and x2, x3. Okay. Any question up to that? You can go home, Ari. So if you have any issues, you can let me know any time of the day or even tomorrow. I'm always at the Math Center. If you want to come over from 10 to 12.